Okay, two more examples and then we're all done. For this one, on a graph of v of t over here, sketch a geometric representation of v prime of 3. Is this the integral or the derivative? And before I tell you, I'd like you to take just a second to glance back in your notes and see if you can figure that out. I haven't told you yet, but you might be able to put it together. So pause the video for a second, see if you can figure it out. Okay. The relevant piece in your notes is right over here where we looked at these notations. Notice the little prime. That shows up over here. This is the little funky S shape. It's actually a summa. It means to add up. And one of the things that we've mentioned several times throughout the notes is that the derivative always takes place at a particular value. So if all I'm telling you is that we've got v prime, we've got a little prime, and I've got a number, what this is really saying is it's saying we're looking for the derivative at, well, there's only one number we've got, so it's got to be that one, x equals 3. So the derivative at x equals 3 means we find 3 for x, and then we sketch that little tangent line. So this is a horizontal line right there. What real-world concept does v prime of 3 represent? Again, pause the video for a second and see if you can figure it out. Well, real-world concept, that's not talking about geometry, that's talking about the rate of change. So the derivative is the instantaneous rate of change of a function. So this is the rate of change of velocity. Again, we have that 3 at, whoops, this should be t. This should also be t. T equals 3. And so now we want to estimate v prime of 3. So this means estimate slope of tangent line. This is a flat line. There is no rise. There is no change in y. So that means 0 divided by anything is just 0. It does still, however, have units. So remember that our units are going to be miles per hour divided by hours, or miles per hour squared. So I kind of put this in here, so it's getting a little messy there, but v prime of 3 approximately equals 0 miles per hour squared. Okay, last problem here. So also looking on a graph of velocity, sketch a geometric representation of this right here. Is it the integral or the derivative? Take a second to look up whether or not you think it's integral or derivative, and then I'll tell you how to pronounce this. So this is, in point of fact, the integral. And all that you saw in the notes is that the integral is just that little symbol right there. This is new because there are the little numbers here. However, we know that the integral is associated with the area under the curve. And we have to have the area under the curve between two numbers, so that would kind of logically imply that that's what these numbers are. They're the only two numbers we've got, so we're probably looking at the area under the curve between 1 and 4. And indeed, that's what this means. It means the integral of v of t from t equals 1 to t equals 4. Right there, from 1 to 4. So what real-world concept does this represent? Well, when we looked at our real-world explanations, we're given a function that involves a rate of change. So velocity is the rate of change of position. So the integral is the accumulation of that change. So if we know a person's velocity, looking at their change in position. So this represents total change in position from 1 to 4 seconds. And now we want to estimate that. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8 whole squares. And then this one's a little bit more than half a square. That's a little bit more than half a square. That's a little bit more than half a square. So if we put them all together, then these two together are going to make a ninth plus a little bit. And when we put all this together, we're probably talking about 10. Now, looking again at the units, this is area, so we're going to do miles per hour times hours, 10 miles. And again, we're probably looking at anywhere between 9 and 11 miles for an estimate.